Let's talk about inductors. Inductors store energy in a magnetic field. I did a video on capacitors which store energy in an electric field. It is linked in the description. Watch it sometime if you haven't yet. Now, magnets, whether permanent, bar magnets, or electromagnetics, have lines of force called flux lines that encircle the bar or rod and run through it. If you apply current to a straight wire, magnetic forces or flux lines will form around the wire, although they are not strong. If you wrap a wire to form a coil and apply electrical current, you have an inductor with a stronger magnetic field because the lines of force strengthen since the coils are aligned with each other. If you insert a ferrous or iron bar or rod, which is the coil's core, through the coil, along its axis, it will intensify the magnetic field according to the permeability of the core material. Permeability is how easy it is for the lines of magnetic force or flux lines to pass through the core material. Now, the more current added, the bigger and intense the electric magnetic field becomes, and vice versa. If you vary the current, the field varies, causing an induced voltage that is in opposition to the applied current. This process of inducing this voltage is called inductance, represented with the symbol L, and the unit of measure is a Henry, symbolized by the letter H. The storing of energy in a magnetic field works like this. In a parallel circuit with a load, which is a device that uses energy, maybe a light bulb in this case, the load offers less resistance and the inductor offers more resistance when you first apply power to the inductor. This resistance to the current flow happens because the inductor is trying to build up an electric field that is resisting the current flow. This is called inductive reactance, measured in ohms, like regular resistance is. Since the resistance of the light bulb is less, most of the current takes the load route through the circuit, and the bulb will be lit. Some of the current takes the inductor route as the magnetic field builds. The higher the magnetic field builds, the more current flows through the inductor, and the light gets dimmer. At some point, the electric field reaches maximum. Once it reaches maximum, the reactance drops to near zero. The inductor acts like a short. Now the current flows only in the inductor circuit branch. When you shut off the power source, the electric field becomes the source of power, so it discharges through the bulb, keeping it lit for the period of time that it takes for the electric field to completely collapse. Then halting the voltage generation because the magnetic field is changing as it diminishes. This induces a voltage. That stored voltage goes through the light bulb branch of the circuit. The process is similar to a rubber pouch that expands as it fills with marbles, the marbles being the voltage. Then, after the marble source is disconnected, the pouch releases the marbles until it's empty. Now, this process happens so fast that you cannot see it. Not like the capacitor, where it happens slow enough for you to see. You can see that. See, it's still glowing. It's still a little bit. This magnetic field storage effect has uses in electric circuits from speakers, metal detectors, solenoids, relay switches, electric motors, and generating AC, as in alternators, magnetos, and other generators, and also in microphones. It also is involved in transformers that are used to step up or down voltage or act as matching circuits for impedance matching. Now, for the purpose of this video, we are making a radio receiver where we are interested in inductors for uses in radios for tuning, filtering, and impedance matching. The schematic symbols for coils are these. So that's it. I hope you enjoyed the video. If you did, please give it a like and subscribe and check out my other videos. Thank you for watching.